Okay then, so we've got our distribution factors and our fixed end moments from the previous video. So we can now start to build up a table for moment distribution. So if we take our grid lines 1, 2, 3 and 4, and we said that our distribution factors initially, so at this joint 2, 3, joint 2 and joint 3, we have distribution factors in the span 1 to 2, and so any difference in moment at this point gets distributed in the ratio 0.429, which was our 3/7 value, and 0.571, which is our 4/7 value, 0.571 here, and 0.429. Those will always add up to 1 around a joint. If they don't, you've done something wrong. And they are the derived from the ratios of the stiffnesses, if you remember. So any imbalanced moment here needs to be distributed, and it will be distributed to the stiffer side of the joint. So more will come into this side than this side, and similarly this side will take more than this side for any imbalance of moment at that point. So we have our fixed end moments, which we said were 0 at this end, which was a pin, 31.875, ended up at this side of the joint. This is before we release them onto the structure, so these are our fixed end moments for the individual spans, which we have imagined separate. They of course are connected in real life, and that's why we need to redistribute the imbalance of moment, because we need to, in real life it will find an equilibrium. And we've got minus 21, so an anti-clockwise moment of 21.25, and then clockwise 21.25 here, and minus 31.875 on this side of the joint, and then 0 at grid line 4, so the other end of the span. So we need a balancing moment. So we've got 31.875 clockwise, so quite a large number, or relatively large number clockwise, and then we've come back anti-clockwise 21.25. So we still haven't come back all the way. We need a balancing moment to get us back to 0 of minus 10.425. So this is our balancing moment. And on this side, we've got 21.25 clockwise. We've come anti-clockwise 31.875. So we need a clockwise moment to balance. So a positive moment of, did I write that? 10.425. That should be 625, I think. Let me just, yeah, so that's equal and opposite. So 10.625 as a clockwise balancing moment. So we distribute that moment in the ratio of these distribution factors. So 0.429 times minus 10.625 is minus 4.558, and 0.571 times that is minus 6.067. Again, the sum of these it will add up to this, because we've split that in the ratio of two factors that add up to 1. Okay. And similarly, this will distribute. This is positive this time, so we will get 6.067 on that side and 4.558 on that side. Okay, we need to, so that is our balancing, distributed balancing moment, and we need to remember that we have this carryover step to do. So our carryover moments coming this way, we don't, or rather they just come to nothing, because this is a pinned end, so nothing can carry over to this side. But on the central span, we need to carry over half of that to here, so that's half of minus 6.067 gives us minus 3.034 as a carryover moment there. And similarly, this carryover moment 6.067 carries over as half of that, which gives us 3.034. Remember, we carry over half of the moment. Okay, so we now can sum all those values. We've still got 0 here, obviously. We have 31.875 minus 4.558, which gives us a value of 27.317, and so that's minus 21.25 minus 6.067 plus this carryover moment 3.034 gives us a total of 24.288. And again, at this joint, 21.25 plus 6.067 minus 3.034 gives us 24.288. On that side, minus 31.875 plus 4.558 gives us minus 27.317. Okay, so we still have an imbalance, and we need to keep iterating until this moment gets distributed to a point where we're in equilibrium. So we're not yet in equilibrium because I've got 27.317 clockwise. I've only got minus 24.288, so I need a further balancing moment of minus 3.029. Okay, and similarly here I've got 24.288 clockwise. I've got minus 27.317 anti-clockwise, so I need a clockwise balancing moment, or a positive balancing moment, which is plus 3.029. Okay, I need to distribute those balancing moments. So these are my balancing moments. I need to distribute those in the ratio of the distribution factors. So 0.429 of this value comes on this side, which is minus 1.299. 0.571 multiplied by that gives me minus 1.729. And similarly, this 3.029 splits in the ratio 0.571 to 0.429, giving me 1.729 that side and 1.299 on that side. Again, no carryover moment to consider here, it just goes to 0. But half of this must carry over, so half of this comes over as minus 0.8 0.865, and half of this comes over as plus 0.865. Okay, and again I add everything up, so I've got 24.288 minus a further 1.729 plus 0.865 here, so that gives me a total of minus 25.152 on this side. 27.317 minus 1.299 gives me 26.018 on that side. Okay, on this side 24.288 plus 1.729 minus 0.865 gives me 25.152, and on this side minus 27.317 plus 1.299 gives me minus 26.018. So I am now starting to converge. Okay, each time I iterate, I'm getting closer to a balance between this side of the joint and this side of the joint, and similarly this side of the joint and this side of the joint. Okay, so I need to keep going until my moment has been distributed throughout the structure such that I have an equilibrium state. Okay, and that you can sensibly stop when you get to within 3 significant figures. So we are getting close to, but not quite there yet. I've got a balancing moment this time of minus 0.866, and I need a balancing moment. I've got 25.152 clockwise, I've got 26.018 anti-clockwise, so I need a clockwise balancing moment of 0.866 this side. Okay, so these are my new balancing moments, and again I distribute those in the ratio of the distribution factors based on the stiffnesses, and I keep reiterating until I finally get a situation where these are, to all intents and purposes, close enough to be considered equal and opposite. Okay, I'll leave it there and leave that for you to finalize for your particular problem.